I'm Deborah Hanus, and today I'm here with Sebastian Hanus to talk about how our journey getting started with deep learning using Keras and NumPy to detect voice disorders. First, to start off with, I'll tell you a little bit about myself. I did my undergraduate and my master's at MIT studying brain and cognitive sciences. So, I started out learning about neuroscience and cognitive science and developing mathematical models of neuroscience and cognitive science. And then I did my master's in reinforcement learning. Then I spent a year as a Fulbright Scholar in Cambodia learning about how education translates into job creation. Then I spent some time working as an early software engineer at a startup out here in the Bay Area. And then I decided to quit life and become a PhD student. No, just kidding. Actually, I loved being a PhD student at Harvard. And I had the opportunity to do all sorts of amazing things, working on a lot of cool projects in machine learning. I interned at Google Brain. And I had the opportunity to mentor and work with all sorts of amazing people like Sebastian. And now I've started a company called Sparrow, which uses software to make it easier for companies to provide their employees with leave.
I started programming when I founded a robotics club in Nebraska with my sister Patricia. Then I did an internship at Sycamore Education, which developed software for under-resourced schools. Then I was a research assistant at the University of Nebraska in Omaha, doing cybersecurity research with machine learning. Then I was a research assistant at MIT, where I worked on the project that we'll be discussing in this talk. So to give you a brief overview, we'll be talking about introducing the project itself and sort of data that we'll have in this example. Then we'll talk about getting started with deep learning and selecting a network to train with. Then we'll apply that back to the project and then discuss some common issues that I dealt with that you can then avoid, hopefully. So started on the sort of data we have. We want to predict whether a patient has vocal trauma just from the vibrations from their voice. So we'll have an accelerometer resting on their throat, and it'll feel the vibrations from them talking. And then we'll have that as a signal in a vector of numbers. And the vocal trauma is from vocal hyperfunction, which is just overuse or misuse of the voice, and it can lead to vocal nodes and other damage. So that blue line is an example of what the utterance might look like. We define an utterance as a period of continually speaking with no more than half a second of silence. And then below that, we have our breath group vector, which just tells us what parts they're speaking during. So let's call that squiggly line at the top one of our utterances. We want to segment out the part where they're actually speaking. So we take our breath group vector, which is the row directly below that. We pad an extra 0 on either end, and then we diff it, which is just taking each element minus the next one, which makes it so you see all the beginnings with ones and all the endings with negative ones, and then we can segment out the utterances. So now Deborah is going to talk about getting started with deep learning.
Okay, so at this point, we've talked about how Sebastian went through the process of processing the voice data. So you have this accelerometer, which gives you some signal, and so then he had to process out these utterances. And then the next step was figuring out, learning some things about deep learning and selecting which neural network architecture he wanted to work with. So we'll walk you through that process here. So first of all, congratulations to all of you for deciding to learn Python, because there are a lot of really awesome libraries for deep learning in Python. Something like scikit-learn is really helpful for a lot of the data processing. It has a lot of more general machine learning methods, but these can be used in conjunction with the deep learning methods as well. Theano, PyTorch, and TensorFlow all give you a lot of really fine-grained control over how you want to develop your architecture. It can take a little bit longer to learn those, but it's nice because if you want to do something really specific, Theano, PyTorch, and TensorFlow will let you do those things. And then Keras is like a wrapper around Theano, PyTorch, and TensorFlow that has a really nice high-level syntax so that you can get started quickly. I highly recommend Keras for a first deep learning project. And then as you get more and more into it, at some point you might need to start working with the PyTorch or TensorFlow or something like this. So to start off with, you can look at this beautiful picture of neurons. As you can see, they're very complicated. They have a lot of connections. There are electrical impulses between going through all of these. And it's really pretty impressive that this is the kind of stuff that we have going on in our brain. So this is a visual textbook version of a neuron. And it explains some of the basics, like we have this soma, and the electrical impulses travel from other neurons through the dendrites. It travels up the axon, and then the axon rests on another soma. And so many years ago, probably like 30, 40 years ago, someone saw this picture, and they were like, I think I can make a mathematical model that does that. So they made this perceptron. And it does indeed have some similarities. Like it has inputs that come in one end, an output that goes at the other end. Something happens to it in the middle. But it is a pretty gross simplification of how a neuron works. But that said, the perceptron is sort of the basis of a lot of the deep learning that we see out in the world today. So the way this works is those x's, those are all inputs. And the input to the neural network can be almost anything. Usually it's numbers. It could be a vector of numbers. It could be a matrix of numbers. When you hear about a neural network doing something with images, usually the way the neural network sees that is it is a matrix of numbers which represent the color which is represented at any given pixel. So if you have a 100 by 100 picture, that is actually going to be a 100 by 100 matrix of numbers representing what the color is at any of those given points. If you hear about neural network reading transcripts, usually the input is going to be numbers indicating whether a word is present, or maybe sometimes the letters themselves might be inputs. But this is usually the way this works. And so then there's some weight. So this indicates sort of like the idea here is like in the previous neuron, some of these electrical impulses are more important than others. Some of them have stronger signal than others. There's not just one amount which the signal travels through. So the weight varies how important that signal is. And then something happens. In this case, it goes through a sigmoid function, which is an activation function. And then at the other end, you have a sigmoid of your inputs multiplied by some weights indicating how important they are, plus this bias term which can shift it in some direction. So in this case, this perceptron is just doing a simple linear transformation. And this is the same idea applies as you make this more and more complicated. But so this perceptron, it's just a linear transformation. It doesn't do any of the amazing and exciting things that we see neural networks doing out there in the world. So we wanted to make it more complicated. So how do we do that? We add more layers. And this is a funny joke, but in general, the way people are getting neural networks to do more and more complicated things is they're adding more and more little fixes to the architecture. Like, oh, this is cool, but I wish it could do this, so I'll add something that does this. And in the process, it's getting more and more complicated. So to start off with, you have like a feed-forward neural network, and you can see that it's a little bit bigger than the perceptron that we started with. The yellow layers are all the inputs. The orange shows the output. The green shows the hidden layers. So we don't necessarily know what's going on in those hidden layers. And then similarly, you can add more layers and get this deep feed-forward neural network. And usually the way that's defined is more than one layer is deep. And so then you can get something that does all of these cool things like this. So a very common task for a neural network might be a classification task. And a simple one is differentiating cats from dogs. So the way this would look is, let's say these are 100 by 100 pixel images. This will be a matrix that is fed in. And the neural network will learn things like cats maybe tend to have pointier ears. And it'll learn the differences between the faces by seeing where the lines around the animal are. And then it can do things like say, this is a cat. Got it. Okay, so this is the high-level overview of how deep learning works. But like I said, there are a lot of different architectures that are involved, and that can do more of the exciting things that are making the news recently. And so to understand those, we'll go over a couple of these in broad strokes, and then we'll point you to some resources for a lot of others, because at this point, there are approximately a gajillion architectures out there. So one that is the convolutional neural network. And this is interesting because what it does is it takes, you can see in this case, instead of having the same number of layers, it actually pools things. And people actually do this too. Like when I look around this room, technically you can say like every time a photon of light bounces off of something and hits my eye, I've seen it. But honestly, I'm not seeing everything. Really what people do is they sort of pool what they see to some extent, and they take a sample from that. So you can kind of see something like that going on in the right here with the input neurons. So it's taking a 5x5 filter of input neurons of information. And usually the way this works is it takes an average of those 5, or maybe it takes a sample of those 5 and says, okay, this is all that I'm going to continue on with. And this kind of neural network is often helpful for recognizing things, because it gets an idea of like the edges around something that it's looking at. So this might be good for like that dog versus cat task, or similar sorts of tasks. And these references along the bottom are all really nice references that sort of step you through step by step how the convolutional neural network does this. Another really cool one is a recurrent neural network. And what makes this one different is it is basically a loop on itself. So before, what we did is just every time step of the neural network only sees what it's seeing at that given moment. You can kind of think of it as like a little time series. So it doesn't have a good sense of all of the data and what's going into it at any given moment. The cool thing about a recurrent neural network is it has this loop. So it sees not only what it's seeing at this moment, but also what it saw in the last step. So it has that information and it can sort of carry it on. And then another one is an LSTM, which is actually a specific type of recurrent neural network. So it also has some sense of time, but in addition to only having recent information, it also has information from a long time ago, because it has this state that sort of is passed from layer to layer. And then when you're defining the neural network, you define certain parameters that define how much of the state you're taking in at a given point. And we also linked some resources that do an awesome job stepping through that as well. And this long-term, short-term memory is the type of architecture that Sebastian chose for his project, because you can imagine that information from an utterance early on might have some effect on an early on utterance might have some effect on a later utterance. So this is what Sebastian worked with, and now I'll let Sebastian tell you about how he used the LSTM to predict focal trauma.
So we have all of our utterances that we segmented out before from just the continuous raw data. And we put those in a matrix and pad them and feed them through the LSTM so that then it can learn to classify patients as either having vocal hyperfunction or not from just them speaking. A couple of tools that are really useful for working with data are NumPy, which is very good for handling arrays of numbers, and a lot of other libraries work with NumPy. And here are just a few links to great resources for getting started with NumPy. And then Keras is the high-level wrapper that we're using to do this without understanding all the low-level intricacies from the beginning. And again, there are a couple of links for getting started. So here's just an example of an LSTM. We want to separate our training data from our testing data so that our model doesn't overfit on the training data and learn the exact data rather than learning general differences between people who have vocal hyperfunction or not. And then we pad it all to the same length so that, since that's what's needed for the model to train on it. And then it's as simple as just making our model, defining various parameters, and then fitting our data to the model. And then we can evaluate on it and get an accuracy. So there are a number of issues that I ran into that are very common that you might also run into, and so I will give you some solutions. You may, since neural networks take so much data to get good accuracy, you probably can't hold all of your data in memory at once. You may have trouble writing all of that data to disk. You may need to run the program a very long time to train, and then you want to be able to understand where your model fails so that you can get a more accurate and useful model. So for running out of memory, you may have a lot of data, but not so much RAM. And so the solution to this is to just train on a little piece of your data at a time in mini batches. And then you may struggle to write to disk. Pickle is a very common library for saving data to disk, since you can just take any binary object, dump it straight into disk, and it's very easy to use. But it doesn't work so well with very large data sets. And so you can use something like joblib or H5Py, which is what I used, which saves it in an HDF5 format, which allows you to store the data hierarchically and just load pieces at a time rather than the whole file into memory at once. And then for managing long-running processes, you'll probably be connecting to some remote machine somewhere else, and you don't want to then disconnect from the server and have your program get killed. And so a couple of easy solutions to this is programs like tmux or screen. A little demo here, you just take screen, open up screen, now you're inside of screen on the server, you start your long-running process, and then you can just detach from it, take your laptop, later come back, open it back up again, reattach, and there your program is right where you left it without it getting killed. And so now I'll pass this over to Deborah for explaining some of the understanding your errors.
So another common mistake that people make is sometimes it can be pretty difficult to figure out what is going on in your data and with your algorithm enough to make sure that everything converges and you get an answer. And so you get your answer, you get some accuracy, you have 95% accuracy, you're like, yes, I have an accuracy and it works, and you're done. But that's the problem, is people think they're done then. And the important thing to remember is that machine learning is all based on data. Like, you come up with these cool architectures, but you can really train it to do anything if your data is not what you're thinking of. So one common example of this is Joybu Umwini is a master's student at the MIT Media Lab, and she did a lot of things with facial recognition software. And so she would make changes to her code using this out-of-the-box facial recognition software. But she could never get it to recognize her face. And it turns out, at first she just got light-skinned friends to test it with her. But then she's like, at some point I've got to test my own code. So she started wearing this white, Phantom of the Opera style mask, which looks nothing like a face. But then the facial recognition software worked for her, because it turns out that the data set had a lot of light-skinned faces. So, people thought that it was learning, this is what a face looks like. What it was actually learning is a face looks like something light with something approximating eyes and a nose and a mouth. But even though, to a human, that looks nothing like a face. But if you don't look at what your algorithm is getting wrong, so if they looked at their data and they said, okay, we have 98% accuracy overall, but what is it getting wrong in these 2%, they probably would have seen, it's getting mostly people with darker skin from minority groups, and it's not recognizing their faces properly. But it's very easy to just get caught up in that one number, that accuracy, and be done with it. So a great way to look at this, some of you might be having flashbacks to an intro stats class, but a great way to start with this is just a simple confusion matrix. So this works very well for a classification task. It can also extend out to larger sizes if you're classifying more things. But for a classification task like Sebastian's, where it was either a patient has vocal trauma. So in this case, a positive would be a patient has vocal trauma. So if they have vocal trauma and they're classified as having vocal trauma, that's a true positive. If they don't have vocal trauma and they're classified as normal, that's a true negative. And then for the false positive would be the prediction is positive, so someone is classified as having vocal trauma, but they're actually normal. And the other one would be someone has vocal trauma, but they're classified as normal. And so by looking at those false negatives and false positives, you can get an idea of what kind of errors you're making, and perhaps if you need to perhaps bias your model a little bit more in one direction or the other to make sure that to make sure that your model makes the same type of errors overall. Then I will pass this back to Sebastian.
I'd like to thank Dr. Marzia Ghassemi for letting me work with her on this project, and Professor Peter Solovich for letting me work in his lab. And these are just a collection of a handful of resources that were really helpful to me and to understand deep learning and then to actually get started working with it. And if you'd like to reach out to us on Twitter, either of us, both of our Twitter handles are there. And I also found that it was really helpful to get help from real people when getting started rather than just following tutorials online when you need something.
Yeah, so so that said, if you have any questions, feel free to reach out to Sebastian or I on Twitter. And it looks like there was a last-minute conversion formatting issue. We'll post slides that do not have teeny tiny font on the resources slide online. We'll probably post them to Twitter. And that said, I think we're ready for questions.
So when we were dealing with the utterance lengths would be different, right?
Yes.
You have a fixed architecture. So what did you do? I'd imagine what are the options?
What I did was I found the longest utterance and I padded all of them to that length. So you could do that, or you could just find some reasonable length that most of them were within and pad them or truncate them all down to that length.
And when he says he padded them with extra zeros, so it ended up being the same length.
So doesn't that change the pattern of what you're trying to teach? Did you see that influence?
I don't know how to answer that.
I'm sorry, what was the question? Does padding it with zeros change the pattern?
It's like if I have a range of really large numbers and suddenly I have ends that are dropping to zero, could that negatively influence what I'm trying to teach
Yeah, so that's why he had the diffing with the 1 and the -1 in the other vector, so that he knew when exactly the utterances started versus when it ended, so that then it was only looking at the utterance.
And what I was told before is that it would just learn to ignore the zeros padded at the end.
Did you, I've seen this in a number of applications where when you choose a model, a time series data, let's go with STM, but then it turns out the CNN actually works better. I've seen that happen across a number of different applications. I don't really know why. Do you have any insight on how that happens, or did you see anything like that? And how did yours perform on a CNN if you tried it?
So these are preliminary results. We haven't tried it with the CNN yet, but that would be a good thing to look at. We'll let you know once we know.
For someone just starting out who has like a regular laptop and wants to do something similar, would this be possible, or would you have to kind of use an AWS instance and get a GPU or something with large enough RAM rather than 16 gigs of RAM?
The problem with the neural networks is they do tend to take a lot of data to learn something good. You could probably train a bad classifier on your laptop, but to work with the types of data that you usually need, it is easiest to use something like AWS. If you don't necessarily need a huge GPU instance, though, you can often get something that is a little bit smaller on AWS and have it cost, have your experiments cost like a cup, more like on the order of a cup of coffee. Karen?
Yeah, so do you have some preliminary data on how it's working so far? You talked about sort of the challenges you've had and how you've worked with it a little bit, but how's it going in terms of?
I don't have results in the slides to show, but I was getting close to 80% accuracy, so there's more work to do.
There are still things to improve on, but it was looking pretty good.
Yes.
Yeah.
I was wondering what your data collection process was like, and if you guys have evaluated on different populations of people, and particularly like gender differences or things like that.
I wasn't involved with the collection of the data, but we did stratify based on gender and occupation, and then made sure that there was a control pair for all of them that were generally similar people, so that hopefully we'd have good data to train on.
So do you think you need to build separate models for different areas, or do you have or was the data pretty similar?
I think that there was a good spread of both women and men in this. Actually, some of the vocal hyperfunction tends to affect women more often. So I think it's possible they might have even been a little overrepresented in this data set. But I wouldn't expect there to be a huge difference between them, but that might be something to look at in the future.
Thank you so much.